Hello everyone, my name is Hazik Kirmani and this is our one more video of the series The Most Expected Archives, and we have our first question from Work Energy Power with us right now, and let's see how to solve this problem. We have been given a student skates up a ramp. Okay, this ramp has been skated by the student in this trajectory. We can see the trajectory that is made here, this line basically. Fine. Okay, and the inclination is 30 degree with the horizontal. She starts at the bottom of the ramp with v naught as the velocity. Okay, fine. So at the bottom the velocity is v naught. Okay, this is the velocity, initial velocity, and he wants to turn around over a semicircular path xyz. See this xyz path, okay, of radius r during she reaches a maximum height of h. Basically this maximum height h is corresponding to this topmost point y, isn't that? Okay, you can see that this h is the front view of this wedge. Okay, while the xyz lies on the plane side of this inclined plane, and he wants to turn, and from the ground as shown in the figure, assume the energy loss is negligible. Okay, so basically with friction and all the non-conservative forces, we can assume them they are not there. So what remains constant? If no energy loss is there, can we say mechanical energy is conserved? Yes, so our mechanical energy is conserved, and the force required for this turn at the highest point is provided by her weight only. Okay, what is it talking about? It says at this y point, the force required. What is the force required? Basically it is this kind of an incline, isn't that? And the particle and this body, the student is doing circular motion, isn't that? While starting from point x only and ends the circular trajectory at point z, isn't that? So at all these points he requires a centripetal force to perform circular motion. At the highest point, if you see, the plane of the circle is in the same plane of that of this plane of the wedge, isn't that? So if we see, this is the radial direction inwards, and what will be the weight of the body inwards there? If this is a wedge, this is a wedge, na? This is the inclination of the wedge. That side we can say it will be mg sine theta, sine 30. Theta is 30 degrees, isn't that? This is the weight component that side, and it is given that weight only provides that force which is required. Which force is required for circular motion? There should be mv square by r as an effective force inwards in the inwards radial direction, and that is given by some force, sometimes weight, sometimes friction, sometimes normal, isn't that? In this case the weight is providing that, so mg sine 30 is providing mv square by r. Fine, this is our first equation. Okay, from here let's solve this. It's a multi-correct problem from JEE Advanced, as you can see, from 2020. Let's see option C and D. The centripetal force required at points x and z is 0. X and z is 0. No, because these 2 points are in the circular path. So even if you start from there or end from that point, if it is in a circular arc, you require centripetal force. So this is incorrect. The centripetal force required is maximum at points x and z. See, the need of centripetal force starts from x point all the way till z point, isn't that? And obviously the direction of centripetal force that is required at every point is different, isn't that? It's radially inwards at every point. Fine, but let's see how much centripetal force do we require. You'll say, sir, we need mv square by r centripetal force. If the mechanical energy is conserved and initial kinetic energy is given half of mv naught square, isn't that energy only being converted into the potential energy because the height is increasing as well as the velocity will be decreasing? Isn't that? Height is increasing, so can we say half of mv naught square only is equal the initial mechanical energy, because initially we are taking this as reference line. Okay, this as reference line. So potential energy we are assuming to be 0. So isn't that equivalent to mg, I'm not saying this h, but any h, for example h dash, any random height h dash, plus half of mv square. What will be the velocity at that point? Make sense? Good. So the more high we go, this component will be more, but this is constant. This already given, this initial kinetic energy, so this has to be less, isn't that? So half of mv square, so that means the velocity at that point, the higher you go, the less velocity you have. So by this can you conclude the velocity at point x and z, because they lie at the same inclination from, not inclination, they lie at the same height from ground, isn't that? And that height is less than h. This is h, na? H height is for point y, and below that every point has less height. Makes sense? So if the height at point z and x is less, can we say velocity at that point is more? If the velocity at that point is more and it is doing a circular motion, couldn't we say that mv square by r, that is required? This is the required centripetal force, okay, to perform a circular motion on a radius r with a velocity v. Shouldn't this be more if velocity is more compared to y? We are talking compared to any point other than x and z, because x and z point in this circular trajectory, they have the least height. If they have the least height, this will be the maximum for them. Okay, velocity will be high. So this option is indeed correct. The centripetal force required is maximum at points x and z. This is correct. Fine. Now if we have this point, can we write the same equation? I wrote this equation for any random h dash, isn't that? Can we write this for y, this y point? Can we say, okay, for y point, half of mv naught square, initial mechanical energy, is equivalent to mgh, because h is given, plus half of mv square, isn't that? The velocity that it has at that point. But we know for the point y, this equation also holds, because it is given the centripetal force is provided by gravity. From here you can replace v square, the velocity at that point, by gr by 2, because sine theta is 1 by 2. So if you put that in this equation, you are going to get A option directly. You can see that, see m and m is going, multiply like both sides with 2, so you'll have v naught square is equivalent to, and if we put this v square here in this equation, because we already multiplied both sides with 2, so this is already gone, so you'll get gr by 2, and if we put like this term, we'll take in LHS, so we'll get exact equation A. So I hope you enjoyed this video. I see you in some other videos also from this series. Till then, bye bye.